Okay, good morning everybody and welcome to our diffusion and osmosis lab. So this is one of the most essential concepts that we have to learn in biology. What is diffusion and what is osmosis? So diffusion and osmosis are very similar conceptually, but one of them is exclusively for water. And that is osmosis. So, what is diffusion and what is osmosis? You have to understand that if you have water is a versatile solvent. So water is most likely to dissolve more solutes than any other solvent out there. If you look at water, this behavior of being a versatile solvent, able to dissolve everybody. Water has many other characteristics that makes it the substance of life. Being a versatile solvent is only one of them. Water has high specific heat capacity in order to help us survive the hypothermia in the summer when it's so hot. Water is adhesive. We use it, in our bodies. We have, our heart is encapsulated with serous membranes full of water. Your brain has a capsule around it full of water. Your lungs, a capsule cushion around it full of water, because water is adhesive. So water is adhesive. Water has high specific heat capacity, meaning that it takes water a lot of heat in order for it to evaporate. Water will evaporate long after ammonia. Even both have similar molecular weight because water has intermolecular hydrogen bond forces. Water is also cohesive. What's the difference between cohesive and adhesive? That's very important. What's the difference between cohesive and adhesive? Adhesive, like adhese, stuck, sticking. So how is water adhesive? Yes.
Adhesive is when water sticks to the surface that it's in, and cohesive is when it bonds to itself.
Excellent. That's exactly true. So let's give examples. Very good. Your definition is perfect. Adhesive is when water sticks to somebody else. Cohesive is when water sticks to itself. Very good. But an example of that would be adhesive is like your heart has a capsule around it full of water known as serous membrane. Your lung has the pleura, serous means full of water. So water is adhesive to the lung. Water is adhesive to the heart. Water is adhesive to the brain, and so on. Cohesive, they say if you have a professional, to be a good professional, you have to be cohesive with your co-workers. Cohesive is when you stick to yourself really well. That's why an insect can walk on water, because the water molecules are so cohesive. But can an insect walk on the surface of alcohol? No. That's why if you leave alcohol overnight, you'll find a lot of insects that are drowning because they thought it's water. It's not as cohesive. Yes.
Sorry, what does it say under adhesive?
So under adhesive, we have high specific heat capacity. When it's too hot, because of this cohesiveness, the water molecules stick to each other so strong that it takes 100 degrees Celsius for water to evaporate. But ammonia is as heavy as water. Yeah, you can tell. Ammonia is NH3. Actually, ammonia is denser than water. Water is H2O. Yet ammonia will evaporate at room temperature in the perfume. Room temperature, ammonia is gone. But for water to be gone, you need 100 degrees Celsius because water is able to have hydrogen bonds and cohesiveness. Is that clear? Now, let's look at the behavior of water in osmosis. Well, before osmosis, the concept that is more more fundamental than osmosis is diffusion. What is diffusion? So if you look at this experiment here, in this experiment, let's say you have a semi-permeable membrane, selectively permeable membrane, meaning that this is gated membrane. Not everybody can pass through. So who passes? Based on what? Based on charge? No. Based on color? No. Based on size, molecular weight, MW. If you can fit through these little pores, you can pass through. If you cannot fit through these little tiny pores, you're not going anywhere. So we have two sides, side A and side B. Is that clear? We have two sides, side A and side B, and they're separated by a semi-permeable membrane. So let's say outside I have 3 elephants and I have 2 cats. And I have here 1 cat and 1 elephant. If I open this door, who's gonna go in? Are the cats gonna come in or are the elephants gonna come in? The cats are gonna come in. Does that mean the elephants don't want to come in? They want to come in also, but the gate is not big enough. So if you put glucose, if you put 500 millimoles of glucose on side A, then you put 300 millimoles of glucose on side B. Then you open this, you allow them to stay for like a half an hour. What do you think is going to happen ultimately? This is just like you have 5 elephants on the outside, 3 elephants on the inside. Do you think the 3 are going to go where the 5 are? Or do you think the 5 are going to go to the 3? Actually, the 3 are going to go to the 5 because that's animals. You know, everybody wants to be with the big group. But in solution, it's the other way around. There is a movement. So diffusion means is the movement of solute particles from an area of high solute concentration to area of low solute concentration eternally, forever? No, until the equilibrium is reached. So now let's apply that there. 500, is 500 more or 300? So the law says there's a movement of particles from where there is a high concentration, 500, to where there is low concentration, 300. Is that clear? So is this movement, like I said, for eternity? Of course not. You're gonna go from 500 to 350 are gonna go. Now you're gonna have 350, and over this side you have 450. Are we done? Of course not. Then another 50 is gonna go to the other side. This is gonna become 400. 50 is gonna be added here. That's gonna be 400 on both sides. Are we done now? Absolutely, because we have reached equilibrium. So diffusion is the movement of solute particles from an area of a high concentration to an area of a low concentration until equilibrium is reached. That is diffusion. Is diffusion limited to chemicals only? What if I had, instead of 500 millimoles of glucose, if I had 500 millimoles of glucose, what if I had 500 millivolt electricity? Millivolt. I have 500 millivolt on one side and 300 millivolts on the other side. Same thing. I'm gonna end up with 400 millivolts on both sides. What if I remove the millivolt and I put degrees Celsius? It's so hot. 500 degrees Celsius and 300 degrees Celsius. Still gonna equilibrate at 400 degrees Celsius. If I had 500 positively charged sodium and 300 positively charged sodium, they both are going to equilibrate at 400 sodium. If I had 500 sodium here, 300 sodium here, and another 500 potassium here, and 300 potassium here, no problem. I'm still going to equilibrate with 400 of each on each side. So I'll have 400 of sodium here, 400 of potassium here, because 500 is going to go to this side. So I'm going to have 400 of sodium, and the 500 potassium are going to move here. So I'm going to have 400 of each on both. So that's diffusion. This is really, really important. Did everybody get that? Now, something that's very important to know. No particle is moving without an energy. What's the energy that powers diffusion? Please don't say chemical energy, because that's ATP. This is known as kinetic energy. Kinetic energy. This is the energy of motion. Energy of motion. The energy of the bombardment. The bombardment energy of molecules bumping into each other, like you know the subway. You know how the people come out the subway? They bump on into each other. That's exactly kinetic energy. So kinetic energy is not expensive. This is the energy of the heat. The heat. So it's very interesting. If you're looking at the rate of these solute particles moving from an area of a high concentration to an area of a low concentration, then you heat it up. What happens if you heat it up? If you heat up this apparatus there with side A and side B. So first you do it at room temperature. And you look at what time does it take for solutes to equilibrate. Let's say it took half an hour. Let's say now you do the same experiment. 500 on one side, 300 on the other, but this time you heat it up. Do you think they're gonna reach equilibrium slower or faster? A lot faster. That proves your point that this was not chemical energy. It was the energy of bombardment, energy of heat. Energy of motion is the energy of heat. Because what is temperature? Is the average velocity of the movement of the molecules. Is that clear? This is diffusion. Diffusion. This is not osmosis. This is not osmosis. This is diffusion. Well, if diffusion is the movement of solute particles from an area of a high concentration to an area of a low concentration, and students stop there. No, that's incomplete definition, because now that sounds like they're going to move endlessly. No, they're going to move until equilibrium has been reached. When equilibrium is reached, then we stop. There's something known as steady state. Steady state. Steady state. What is steady state? Steady state means even though we have 400 on both sides, when we have 400 on both sides, steady state means one bounces here. Now you have 399, then another one and 401 here, then one bounces back, and then you have 400 now. then another one bounces here. So steady state means there's still movement. It's not like they're going to be locked in. 400 on this side, 400 on this side, no movement. No, there is a movement, but it's an equal movement. If one jumps there, the other one is going to make up for it. Is that clear? This is diffusion. This is not osmosis. What is osmosis then? Now, let's look at our same apparatus again. If you look at the apparatus again, now you have on one side 500 millimoles of glucose in water. That one was in water also. Glucose in water, dissolved in water. And on this side, this is side A, 500 millimoles of glucose in water. And this is side B, 300 millimoles of glucose in water. But this time, what's different this time? There's something that is different compared to before. What's different? What's different if you compare the diffusion apparatus to the osmosis apparatus? Yeah.
Will water move from a low to high concentration?
So yeah, but we haven't begun the experiment yet. We're now looking at comparing the two apparatuses. Before, 400 millimoles of glucose and 300 millimoles of glucose. The membrane pores were bigger here, weren't they? They would allow for glucose to pass through. Now look there. They're still pores. They're microscopic pores. They're not big to allow glucose to pass through. They're only big to allow who to pass through? Water. Now that's the difference now. Before, when the pores were big enough, we will have diffusion. But now the pores are not big enough. The pores are not big enough to allow glucose to pass, but they're big enough to allow water to pass. So you're going to start off with two solutions like that. Oops. Two solutions. You're going to start with two solutions like this, where you have water, 500 millimoles of glucose dissolved in water, 300 millimoles of glucose is dissolved in water. But glucose cannot move, but there's still an osmotic pressure, meaning that there's a disparity and inequality of solute particles. So what's going to happen now, we said water has a versatile solvent capacity. So water is going to go from an area where there is low solute concentration, 300 is much less than 500. So water is going to go from 300 to 500, and you're going to end up with something that looks like this. The water level at the 300 is going to drop, and the water level at the 500 is going to go high because water moved from an area of a low solute to an area of a high solute concentration. Is that concept clear? So osmosis is the movement of water, only water. If you replace glucose, if you replace water with alcohol, you dissolve sugar in alcohol. Will alcohol move from an area of a low solute concentration to an area of a high solute concentration? It will not. Only water does that. So osmosis is the movement of water, exclusively water. Nobody else can do osmosis except water. It's the movement of water from area of high, from an area of low minus solute concentration to an area of a high high solute concentration until equilibrium, until osmotic equilibrium is reached. Is that clear? Are we clear? You will see that your plasma membrane is that particular type of a selective barrier. It allows some proteins to pass through, some electrolytes to pass through, and allows water also. So let's look more into it. There you go. That's what we were saying earlier. Diffusion in red, osmosis in whatever color that is. Diffusion and osmosis. Diffusion is the solute will move from high. If you spray perfume at this corner of the room, you will see that it's gonna spread to the far corner where there is no solute particles, where there's no perfume particles, right? Is that true? Okay. Osmosis is different. Osmosis now, this is what we just said. The membrane is so tiny, the pores are so tiny, they don't allow these big bubbles, these big sugar particles to pass through. So now look what happened here. You guys paying attention? If you look here, water has shifted down from now you have two sides. That's side A to the left of the barrier and side B. So water moved from where we had 3 particles to where we have all these particles. So the water shifted to the other side. Do you see that? Do you see that? Okay. So solvent, water will move from low to high. You see that your plasma membrane is the same way. Your plasma membrane, if you look now, the plasma membrane has ion channels, protein pumps, aquaporins for water. Aqua allows the movement of water. And GLUT. What is GLUT? GLUT is glucose transporter. GLUT is glucose transporter. So those are the cell membrane phospholipids. So the plasma membrane is like a bilayer leaflet. It's like a hybrid. You know a hybrid? A hybrid is like a 2-in-1. Is a hybrid. A hybrid is a 2-in-1. So if you know a hybrid car is like gas and electricity, two different energy sources. If you have a hybrid membrane, it has a polar head phosphate and a non-polar tail. Polar head phosphate and a non-polar tail, a lipid hydrophobic free fatty acid chain. And you don't have one hybrid, you have 2. There we go. There they are. The top here you see? Those are the phosphate heads facing water. There's 2 water on the extracellular environment and water in the cytosol, in the inside, in the intercellular environment. And you have those non-polar tails. You see? Those are the polar heads and those are the non-polar tails. Non-polar is like this is a fat, oil, butter. This is a butter. Remember the Sudan oil red? Yeah, this is all going to be detected by the Sudan. But if you look on the top, this is the polar head. Now that dissolves in the water. So you need to know the structure of the plasma membrane. It has a bilayer leaflet, a hybrid, polar heads, and non-polar tails. And you have 2 of each. 2 layers, polar heads and non-polar tails. Those are the phospholipids. Well, If you are, here, red is the butter, is the non-polar. If you are polar, can you cross the bilayer leaflet? If you are polar, can you cross the bilayer leaflet? Absolutely you cannot. So you need a tunnel. Like, when you're driving and you come to the ocean, can your car turn into like a submarine and just like go through the water? Obviously not. So that's the same thing. Sodium, potassium, those are charged particles. So that means they're polar or non-polar. If you are charged, you have a sign on you. You're not neutral. You're either positive or negative. So you are polar. You know the pole of the battery, one is minus, one is plus? So if you have a charge on you, you're polar. You dissolve in water. But the bilayer leaflet is significantly polar or significantly non-polar? It has two tails non-polar, one head polar. Is it majorly non-polar or polar? It's completely non-polar. So that's why if you're non-polar, if you're made up of lipids like oil, if you're made up of these hormones like testosterone, estrogen, those are made of cholesterol. Cholesterol is non-polar, so it goes right through the plasma membrane. Doesn't need a tunnel. Right through. But water, can it go right through the oil? Can water go right through the non-polar segment of the plasma membrane? It cannot. So it needs a tunnel to pass through. So this is the fatty acid. We have dehydration, meaning that we remove water. So a fatty acid is made up of glycerol and 3 fatty acids. 1 glycerol and 3 fatty acids. Is that clear? 1 glycerol, 3 fatty acids. You see that? This 1 glycerol and the 3 fatty acids are bonded by a temporary bond. This bond, we can break it and we can assemble it. The bond is made up of this water. If we want to hook them up together, we remove water. You see, that's called dehydration. We make an ester bond. You see an ester bond, oxygen between 2 carbons. And if we want to break it down, we do something known as hydrolysis. We restore the water back and then we cleave the bond between the glycerol and the 3 fatty acids. There's a transport across the membrane. And this is the concept that we need to understand. Diffusion. Students say, diffusion doesn't require energy. That is grossly incorrect. It doesn't require chemical energy. Active transport requires ATP, chemical energy. But diffusion does not require chemical energy. But does that mean it requires no energy? What's the energy that is required for the movement in diffusion? Yeah. Kinetic energy, the energy of heat, bombardment energy. Okay? So if you look here, in diffusion, we talked about that. If you have a 10% solution on one side and 20% solution on the other side, what's going to happen? The purple, water is in blue. Purple is your glucose. You will see that the big blue is going to move from where there's 20 to where there's 10%. Same way we had 500, 300, they both became 400. Now 20 and 10. So 5 is going to go to the other side. Now we have 15 on both sides. This is known as equilibrium, steady state equilibrium. If you look here in the plasma membrane, you will see that this is the bilayer leaflet. And there's a nice video in here. Diffusion.
To get started, you have to get it on.
Diffusion is the net movement of a substance from a region of high concentration to a region of low concentration. Let's use this sugar cube and beaker of water as an example. When the sugar cube is dropped into water, it begins to dissolve. The sugar molecules in the cube move from an area of high concentration to areas of lower concentration until the molecules are evenly distributed. This type of motion is known as diffusion.
Okay.
The plasma membrane is the gatekeeper of the cell, allowing certain substances in and out of the cell at certain times in certain amounts. Diffusion is a process in which substances move across a membrane from an area of high concentration to an area of lower concentration, or between areas of opposite electrical charges. This is called the electrochemical gradient. Small, non-charged particles, primarily gases such as oxygen and carbon dioxide, can diffuse through the plasma membrane by moving in between the phospholipids in the bilayer. However, the cell needs to control what enters and leaves, and so transport proteins aid in the selective movement of other molecules across the membrane without the input of energy. Through facilitated diffusion, larger molecules, polar molecules, and charged ions use channel proteins embedded in the bilayer. The transport of other substances requires a special carrier that will bind the substance on one side of the membrane, which triggers a conformation change in the protein carrier, causing it to release the substance on the other side.
Okay, diffusion is not only limited to liquids. You know, gases diffuse also. When you take a deep breath, how did oxygen go from the air into your blood? So oxygen is dissolved in air. You take a deep breath, it's gonna go in the lung, and from the lung you have a diffusion of oxygen from your lung into the blood. What is facilitated diffusion? Well, facilitated diffusion is a form of diffusion, meaning we're moving from an area of a high concentration to a low concentration. Diffusion is diffusion, whether it's facilitated or non-facilitated. So we're moving from an area of a high concentration to an area of a low concentration. The only difference now is when you're at the plasma membrane. Remember what we were saying earlier. If you have 10 elephants outside, it's too crowded, they want to come to where there's only 2 in this big spacious room, but the door is not big enough. Facilitated transport would be when you have like a huge elevator that is able to like bring them all in. So the same thing, glucose. You have 500 millimoles of glucose outside the cell and only 200 on the inside. The diffusion pressure is from outside to inside or inside to outside? What's the direction of the diffusion pressure? If you have 500 millimoles of glucose on the outside, 200 on the inside.
Pressure from outside to inside.
Exactly. The pressure of the glucose is from the outside to the inside. But the plasma membrane is too tiny. So we need a facilitator. A facilitator would allow for the otherwise impossible movement of these glucose molecules. So this is everybody please look at the facilitator.
In the process known as facilitated diffusion, a special carrier protein with a central channel acts as a selective corridor which helps molecules move across the membrane. These special carrier molecules that form the protein channel bind only to a specific molecule, such as a particular sugar or amino acid. Once the molecule binds to the carrier protein, this protein helps or facilitates the diffusion process by changing shape and moving the molecule down its concentration gradient through the membrane into the cell where it is released. Facilitated diffusion is similar to simple diffusion in that both involve movement of molecules down their concentration gradient, and this movement is carried out without any input of energy. However, in facilitated diffusion, the movement of molecules will only take place if it is facilitated or helped by a special protein carrier in the membrane. Facilitated diffusion can occur in either direction depending on the concentration gradient. If there is a higher concentration of the particular molecule inside the cell, the same carrier protein would then transport the molecules out of the cell.
Okay, active transport is different now. Active transport does require energy in the form of ATP. In the forms of ATP. And why do we need energy in the form of ATP? You know, when you're rolling downhill, do you press the gas? No, the car just rolls downhill. But if you're going uphill, do you press on the gas now? Absolutely, because you need more energy. You need to burn the fuel. The fuel is chemical energy. You know, gasoline, that's chemical energy. Same thing your cells. If you want to transfer something against the concentration gradient, going uphill, you're going to need energy for that. Imagine, you know Black Friday? Black Friday when like 500 people try to make it inside the store? Well, that's an example of diffusion or active transport. When 500 people are trying to go inside the empty store where there's nobody in there. That's diffusion, because you're moving from a high concentration area, it's like 500 people out there, to there's nobody inside. Now imagine on Black Friday, right when they open the gates, there's somebody standing at the door like The Rock. You guys don't know The Rock? You guys know The Rock? Imagine The Rock is there, and for every 10 people that move in, he would grab all of them and send them out against the 500. I don't think he can do that, but let's assume, for all intents and purposes, he can do that. That's active transport. So your sodium potassium ATPase is The Rock that does that. Where all the sodium who's outside, there's a lot of sodium on the outside of the cell, trying to like Black Friday come inside the cytoplasm. But once three sodiums leak in, the sodium potassium ATPase is gonna grab them and throw them right out. That's an example. So something as hard as that, you absolutely need ATP for. So active transport, you're gonna need ATP for. So that's the experiment we're gonna be doing. Everybody pay close attention. Those beakers in here, they have hydrated dialysis bags. Those dialysis bags are your plasma membrane. These are the selectively permeable membrane. It looks like it's a bag. First of all, it's open-ended. Sometimes we clip it in the bottom, sometimes we tie it. But this bag, when you tie it or clip it from the bottom, like this, the holes are microscopic. They are so tiny you cannot even see them. And actually, it's a tape. That's why we hydrate it. Hydrate the tape. What does hydrate mean? You wet it. When you wet it, you can now open it. You clip one end and you put the substance on the other end. Is that clear? Okay. Then you're gonna put this dialysis solution in some solution of a known osmolarity. If the osmolarity is high on the outside and the osmolarity in the dialysis bag, let's say the dialysis bag is 10% solute, on the outside is 30% solute, and the pores are only big enough for water to move in. We did that with Sudan and Burette and all of that. What do you think is going to happen? If you dip a 10% in a 30%, is the solution Hyperosmolar or hypoosmolar? Compared to the dialysis solution. It's hyper. Yeah. So it's hyper on the outside. On the inside is hypo. Yeah. So if you're referring to the dialysis bag, it's hypo. If you're referring to the outside solution, it's hyper. Very good. So water now is gonna move from 30 to 10 or 10 to 30. Is water gonna move from 30 to 10 or 10 to 30?
10 to 30.
It's from 10 to 30. So what's gonna happen to the bag? It's gonna shrink, shrivel up. So if you have a red blood cell, you see this is happening with your red blood cell. Let's say I have a red blood cell. What's the osmolarity inside the red blood cell? It's 300 milliosmoles. 300 milliosmoles. 300 milliosmoles. You have three solutions, A, B, and C. This is very, very, very important. Let's say you have three solutions, A, B, and C. And you dip in the three solutions a red blood cell. In the three solutions, you dip 3 red blood cells. On solution A, the red blood cell coincidentally happens to be on a 300 milliosmol, so the inside and the outside are equal. What kind of solution is that? Isotonic. Isotonic solution. Like an isosceles triangle, they're equal. So the water level, the water rate of osmosis is going to be, are you going to have more water flowing out from the red blood cell? That's the red blood cell, RBC. That's the red blood cell, RBC. Red blood cell, RBC. If inside and outside are equal, are you going to have more water flowing from inside to outside or from outside to inside? Or are they equal? So the water level is going to be moving to the inside of the red blood cell and leaving it at the same rate, meaning that the red blood cell is going to be the same size. It's not going to change. Let's say now you drop the 300 millimolar, the 300 milliosmol in a 30 milliosmol solution. What's going to happen to the water? Is more water going to flow in, or is more water going to flow out, or are they going to be equal?
The water will go into the cell.
The water will go into the cell, and that's going to cause the cell to swell and burst and turgor, because the solution is hypoosmolar. That's the hypoosmolar solution. If you look in the last scenario, you drop the 300 milliosmol red blood cell in a 3000 milliosmol red blood cell. What's going to happen to the water? The water in the red blood cell is going to go from inside to the outside. So the red blood cell is going to shrivel, is going to crenate, and shrivel up. Is that clear? So, the substances that can move through a selectively permeable membrane, they're going to be put inside the dialysis bag. And dialysis tubing is a selectively permeable membrane that is used to separate large molecules from small ones while allowing the small molecules to pass through while restricting the larger ones. This will visualize how substances move in and out of the cell. Okay, so let's begin the experiment. Remember, we talked about this. Osmosis is when you have two regions, but one region is too big to pass through. So the water is going to go from where there is less solute to where there is a lot of solutes. Isotonic, hypertonic, hypotonic. We discussed that. In isotonic, the rate is going to be the same. In hypertonic, there's gonna be more water flowing out, so it's gonna shrink, and in hypotonic, more water is gonna flow inwardly. That's an isotonic solution. Now it's in equilibrium. That's a hypotonic next to a hypertonic solution. You see the water is gonna move to where there is more solutes. If you drink too much water, that happens to the people who run the marathon. And once they cross the finish line, they start drinking water like crazy. What happens? Their blood becomes hypoosmolar, and the water is gonna go inside the red blood cells. This is very important.
You know the feeling when you realize you bought things you'll never use? Sound familiar? Then try Vinted. These boo.
See what happens? When you drink too much water, the water is gonna go inside the red blood cell. You see they're getting bigger and they're expanding. They're gonna explode. This is the water in a hypertonic solution. That's the water in an isotonic solution. It's not gonna change. Let's look at water. You see, isotonic solution, it will not change. But if you put it in distilled water, water is going to go inside the red blood cell. It's going to blow up. Look, they're going to burst. Did you see them bursting? They all bursted. You see? Do you see that? Why did they burst? Oh boy. This is what happens to the marathon runners. Because they're so dehydrated. They're so dehydrated, they drink a lot of water, the water goes inside their red blood cells explode. Is that clear? Okay, so let us now isotonic, hypertonic, we discussed that. Okay. So let's begin the experiment. Everybody please turn to page 71, and do not forget, we're always going to have modified activities. So don't forget those. We are doing procedures 9.1 to 9.5. No 9.6, no 9.7, but 9.8. This is your guide. You must begin procedure 9.4 at the beginning. We start with 9.4 first. Everybody start with 9.4 because it takes a lot of time to complete. Okay? Begin with 9.4, then return to 9.1, 9.2, 9.3, 9.5, then go to 9.8, and we're done. No 9.6, no 9.7. Make sure that you refer to this modification. It's very important. When you get to 9.2, you're going to use only two halos. The potassium permanganate, and it tells you the molecular weight is 158. Methylene blue has a molecular weight 320. So obviously 320 compared to 158, you know which one weighs more. There will be no malachite green, so we're going to skip that part. For procedures 9.3 and 9.4, refer to this document. The dialysis tubing is already pre-cut and pre-soaked for you in this beaker. There's 6 pieces per each group for procedures 9.3 and 9.4. And for 9.4, there's 3 bags in the 1% sucrose. Okay? When you guys are using the weight, use the weight boats when weighing the bags. Do not put the bags on the actual scale because the sugar is gonna latch and it's gonna get very sticky at the surface of the weighing scale. Directly on the balance pan, the sugar solutions are gonna get sticky. Okay? Alrighty. So let's begin with 9.4. Everybody start with 9.4. Goggles on. Please make sure your goggles are on.